whole research is actually part of what I've been doing as a postdoc here at Western, together with our very chair over there. And this is why you see both ladies' name and also the Western logo on the slides. So we just recently got around to writing everything up nicely, and yeah. So a good portion of this work was done here at this university. Okay, the whole work is about matrix fractions. So what we were looking at was the Lu decomposition. So I guess most of you know the Lu decomposition from numerics, or maybe from the first year linear algebra courses that you have to teach. So if you do Lu on a computer algebra system, you usually want to have exact results. So this talk is about Lu decomposition with exact entries. In this case, I've got numbers, because numbers are just much easier to fit on the slides. But everything which I say here would work for other domains too. For example, matrices with polynomial entries, univariate, multivariate. Basically, every integral domain is possible. Okay, so usually when you do an Lu decomposition, you would perform Gauss Elimination, and just to get you in the right mood for the other methods, I put it here on the slides. If you do Gaussian elimination, as you all know, what we do is we first choose a pivot, then we divide by the pivot, getting a nice 1 here, and then we use this one to eliminate all the entries in the same column, getting a matrix which looks like this. There's only one non-trivial entry in that column, and then we just repeat the same with this submatrix here, where we ignore the first column and the first row. So again, we choose a pivot, and we eliminate everything. And if you go on like this, you'll eventually end up with an upper triangular matrix like this here. Now, so that's the standard algorithm, but that's not how computer algebra systems usually do it, because there is a slight problem, and that is that you have to work with fractions. Now, as everyone who's currently visiting middle school can tell you, working with fractions is not that easy. And the same is true for computer. So you either have the choice of keeping your fractions in reduced form, which means that you have to compute GCDs every time you do an arithmetic operation, or you don't do that, in which case your numerators and denominators become longer and longer. So people have been looking for other methods in order to do this kind of elimination that avoids fraction. The first method, the easiest one to come up with, is known as the division-free method, or just cross multiplication. We start with the same matrix again. We choose the same pivot, but instead of dividing the first row by the pivot, we simply multiply all the other rows by the pivot, ending up with this matrix here. Now, every entry here is divisible by the pivot, which means that when we eliminate them, we only ever need integer multiples of the first row. And that way, everything which we do is done in the integers. And we can, of course, just repeat this with a submatrix here, choose the next pivot, do the elimination. So here's one more step, multiply by the pivot, eliminate, and if you continue, you'll get an upper triangular matrix which does not contain any fractions at all. So, seems like we're doing a bit better now. However, as you can see, the numbers are getting fairly large. So what this is here, I think about 13 digits. And this is just a 5 by 5 example. If you do larger matrices, you will have some really, really huge numbers. And that, of course, is also a problem, because working with huge numbers costs computation time. And yes, in fact, you can show the numbers. The size of the numbers will grow exponentially. So for large matrices, this is really impractical. And for a good enough measurement of size, the same problem exists for polynomial matrices and other domains. But there's a way out, which is known as Bareiss algorithm. or more precisely Bareiss single-step algorithm. There are several versions of this. I'm using the single step here. And what you have to notice is that if you look at the matrix on the last slide, then everything in the last 3 rows, so all the highlighted entries, are actually divisible by 6. So we can easily see that they're all even, and you can then check that they're also all divisible by 3. So everything here is divisible by 6, meaning that because in the end we are thinking about, this is just a replacement for fractions, right? We don't want to do fractions, but we think about the computations as being done over the rational numbers. So we can just cancel the 6 here without really changing our normal form. So, and if you do that, the entries become a bit smaller already. And then you look at the next entries and you see that those here are also divisible by 24 in this case, for example. So you can make it smaller again. And actually, this observation always works. It's described in this paper by Bareiss. And the basic idea, I would like to illustrate it just with an abstract 3x3 matrix here. So let's start with this 3x3 matrix, and let's execute the cross multiplication algorithm. So we choose A as our first pivot, multiply all the other rows by the pivot, and now subtract B times the first row from the second row, G times the first row from the second row for the elimination step, ending up with this matrix here. You can't see any obvious factors yet, but if you do one more iteration, so if you choose this pivot here, then there will be a factor appearing. So we multiply by the pivot, we do the elimination, and now if you look at this entry here, you will see if you expand the products, everything will be divisible by A except for the product of these two and of these two. But those are the same numbers, and so appear with an opposite sign. So they just cancel out, and everything which remains is divisible by A. And of course, if this was a larger matrix, then every entry down here and over here would have this form. So everything in this submatrix will be divisible by our first pivot A. And if you go on, you can actually prove that the second pivot, so AE minus BD, after one more step, so it had a 4x4 matrix, after one more step, everything would be divisible by AE minus BD down here. And after the third step, everything would be fourth step, everything would be divisible by the third pivot, and so on. And this is known as Bareiss single-step algorithm. So here, I just put it on the slides. I choose to represent it in a recursive way. If our matrix is empty, we don't have to do anything. Otherwise, we choose a pivot. We multiply all the lower rows by the pivot, eliminate all the entries, and then our observation tells us that all the lower rows will be divisible by the previous pivot. So we can just divide it out and then go on with the algorithm recursively on the submatrix. And this way we keep the entries nice and small. So here's the same matrix again, and this time I'm applying the Bareiss algorithm. So we need 2 steps in order for the first factor to appear. And by theory, we now know that everything in this submatrix here should be divisible by the first pivot. And you can easily check that this is the case. We divide out the first pivot, obtaining much smaller entries here. We go on one more step. Now everything down here should be divisible by 24, and indeed it is. So we can cancel 24, getting smaller entries, and after just one more step, we arrive at the final matrix, and you can see that the entries are much, much nicer than before. In particular, I just have 5 digits here, where before I had 13. So the entry size shrinks a lot, and it is actually possible to show that the entry size with this algorithm grows only algebraically. So much, much better than the naive cross multiplication. However, So this is where David and I started. So far everything is known and has been the standard for years. I mean, Bareiss paper is from the 60s, from the late 60s, and this algorithm is implemented in every major computer algebra system. And David and I happen to be looking at this actually as a project for a student of David's. And then we noticed something. So if you look at this matrix closely, you will see that there are still some factors left. For example, this row here, you can immediately see that everything is divisible by 3. Here, all the entries are even, so everything here is divisible by 2 at least. Here, everything is divisible at least by 10. And in fact, if you do the exact GCT computations, you'll see that the common factor here is actually 4, and here it's 190. So there are still a lot of common factors left in this matrix, and that got us interested. So we wanted to see whether this was just an artifact, maybe just particular examples, or whether there was a reason behind that. I guess I have one more example. Yes. So here's just another example to show you that it's not only integers, but this is really a general thing. I take a matrix of polynomials over the field with 2 elements, just to keep the coefficients small. So this is the input matrix. I run the Bareiss algorithm, ending up with this output matrix. And if you compute the GCDs for each of the rows, you will see the first 2 rows do not have common factors, but the third row has a factor of x squared plus x. The fourth row also has a common factor. Well, okay, the last row is not really interesting because there is only one entry. But we do get common factors for these 2 rows. And this is not just a special example again. I literally just put a random matrix here, and that's what's come out. So this is a typical case. In fact, this is an experimental math conference. We actually did some experiments. This graph here is for integers. You can see here's the size of the matrix. So for example, 20 by 20, 40 by 40. We computed how many were, yes, 400 matrices for each case. Ran Bareiss algorithm on them, and then counted the common factors for each of the rows, except for the last row, of course, which has only one entry. And you see that the numbers of common factors is steadily growing. So there's a lot of factors which Bareiss algorithm does not find. And I have a very similar looking picture of polynomials too. So again, it's just easier to do the experiments with integers, but you get the same pictures for polynomials. There's also a linear growth of factors. Okay. So this is the starting point for our project. We wanted to know where do these factors come from. And yes, before I go to this theory, there's one more background information. This is actually work of David. If you look at the Bareiss algorithm and you look at the matrix transformations, you can write them down as elementary matrices, and if you rearrange them a little bit, you can get this very nice form here. So you can decompose A as subpermutation matrix times a lower triangular matrix times a diagonal matrix to the minus first power times an upper triangular matrix, and then you probably also need another permutation matrix. So you can ignore the permutation matrices, and you basically just got the Lu decomposition, except that all the denominators are collected in this diagonal matrix D. So all the matrices U and L as well as D to just contain are fraction free. There are no fractions in those matrices, and also the computation of these matrices is fraction free. And yeah, the basic idea is use Bareiss, but then do some clever rearrangement of the transformations. Okay, I'm mentioning it because I will be talking about the L matrix later. Okay, so I'm going to present 2 ways of why common factors appear. The first is the more theoretical result, which connects common factors to the so-called Smith form, or Smith-Jacobson form. For this, I need to consider a principal ideal domain. So multivariate polynomials are out for the moment, because that's where you have the Swiss form. And over such a domain, you can show that for every matrix, you can transform it into a diagonal form using some unimodular transformation matrices. And this form is basically unique, given the condition that the entries on the diagonal divide each other. It's called the Smith normal form, or Jacobson normal form, or Smith-Jacobson normal form of the matrix of A, depending on whom you want to give credit. And what we are interested is the so-called determinantal divisor. And the case determinantal divisor is just the product of the first k diagonal entries. Like I told you, they're essentially unique up to multiplication by a unit. So also the determinantal divisor is unique up to multiplication by a unit. And we have linked those determinantal divisors to the common factors. So we take this Lu decomposition of our matrix, and then it turns out that the case determinantal divisor of A will always divide the case row of U and the case column of L. So this shows that common factors are not just some random effect, some fault in our experiment, maybe some problem with a random number generator, but they are really intrinsic to the problem. As soon as you have a non-trivial Smith form, there will be common factors. Yes, I also sketched the proof here. So for those who know Bareiss algorithm, you will know that you can actually express all the entries in the output matrix U as determinants of entries of A, and also the determinantal divisors. I mean, they do have their name for a reason. They can also be expressed as determinants, and if you can match it together and see that you must have this representation here. Okay, so this is one source of common factors here. It's not a very practical source, however. It just tells us that there must be common factors, but I don't think that anybody's going to compute a Smith form just in order to remove common factors from a Lu decomposition. So we looked a bit further, and we found another way of predicting common factors. So now I can actually relax the restriction on my domain. Here I only need to compute GCDs, so a unique factorization domain is fine. In particular, the multivariate polynomials are in again. And what we did is we were looking closely at what happens at cross multiplication. So let's say we already did some iterations of Bareiss algorithm, and we are at this state now. So P was the pivot of the last iteration, and we're looking at this submatrix down here. Let's say A is non zero, if we choose it as a pivot. Then we multiply this row by A and subtract B times the upper row, giving us this representation here. So this actually you can see quite clearly why it's called cross multiplication, because I multiply this by this, this by this, subtract it. However, what you can also see here is that if A and B have a common factor, then this common factor will also be a common factor of the entire row. Here is a formula. Now, this is a bit too much because we still have to do the exact division by P, which means that in order to be careful, we just take out all the factors which are also in P. So we end up with a common factor for this row here of the form GCD of A and B divided by the GCD of A, B, and P. And this is guaranteed to be a factor of this row. The nice thing about this representation is that we only have to do 2 GCD computations in order to compute a common factor. I mean, if you have a long row with, let's say, 100 entries, we can still just need to do 2 GCD computations. We don't have to compute the GCD of all the entries. So it's a lot cheaper to compute to get factors in that way. As we will see on a few slides up, we don't get all the factors, but we do get sufficiently many with this really simple computation. But before we go there, I would just like to mention that all these entries, A, B, and P, actually do turn up in the L matrix. So you don't have to do any bookkeeping during the Bareiss algorithm. You can just take any implementation of the Bareiss algorithm, which you happen to have lying around already, and then look at the matrix L after the computation and compute the common factors from there. So if you go to Maple or Mathematica or whatever you use, just use the normal Lu decomposition algorithm, and you can always remove the common factors afterwards. And yes, if you the similar consideration actually works for the entries of L. So this is on the next slide. Using some entries of U, you can predict common factors in the columns of L. So this is what we did for U, and this is the analogous statement for L. Okay, so here is the example with the polynomials again. And this was our output matrix. This was the actual factors which we computed. And here's what our prediction gives us. So you see, we didn't get this polynomial from the prediction. Basically because here's just ones. And we also did not get the complete polynomial here. But we did get a quite large factor with the prediction. And in general, here's the same graph as before again. The same common factors in the integer matrices. And now I added another line showing those common factors which we predicted. And it is consistently about 40% of the factors. So that's quite interesting, I think. So we actually do get a lot of those factors. And thanks to Kevin Hare, who will be speaking later in this session, we actually, at least for the integers, can tell you how likely it is that this GCD here is non-trivial. So we get a value of approximately 26%, which means that around in one quarter of all the elimination steps, a common factor will turn up, at least for integers. I also did some experiments with polynomials over a finite field, and you can see that the probability of a common factor turning up in that way gets lower, but at least for small primes, you still have a lot of common factors occurring in that way. Okay, there's a few more results. So you know that there's different matrix decompositions. In particular, there's the so-called QR decomposition. And you can define a fraction-free version of the QR decomposition. It's called the theta dr decomposition, where it's the same idea again. You collect all the denominators in a diagonal matrix D, and the product of theta and d to the minus 1 would be the Q matrix in the standard decomposition. So there is a link between the LDU decomposition and the QR decomposition. So this was found in the 90s. If you take this matrix here, A transpose times A, and you add another block of A transpose, and you do an LDU decomposition, you get a factorization from which you can get all the components of the QR decomposition. So this was known for the normal non-fraction-free decomposition, and has been extended to fraction-free decomposition as well. Here's an example of that. And when we tried out those examples, we noticed that there will also be some common factors in our output here. So you see immediately that everything here is divisible by at least 2. And some of you might actually be able to compute that everything there is divisible by 282. So there's quite a large factor in this column. And when we did the experiments, we found that this is really common. The last column of theta always had a rather large factor. We were wondering, where does this factor come from? Where did we see those numbers before? And, well, it's actually quite easy. That number is just the determinant of A. Yeah, you might be able to see it from this. It's a small example. And as I will show you on the next slide, the determinant of A always comes up in this column here. And we know that it will also be a factor of the entry of D, which means that we can always cancel it and arrive at much smaller matrices. So let me just briefly display the theory. Actually, we can tell you exactly what the last entry of the last column of theta will be. It will be -1, the factor of -1 times the determinant of A times the subdeterminant of A. And this is actually all I wanted to say. So we have looked again at the Bareiss algorithm. We noticed that there were a lot of common factors, and we can explain them. Not all of them yet, but a large portion. Thank you very much.